All right, in this lesson, we're going to look at factoring sums and differences of cubes. We've looked at this before, either in Algebra 2. We may have looked at it even this year a little bit. But of course, after we do that, we're going to want to actually solve equations that involve sums or differences of cubes. So let's take a look at these patterns. For a sum of cubes, if we have a cubed plus b cubed, if we can recognize that we've got the sum of two things that have been cubed, then the pattern is going to be a plus b times a squared minus ab plus b squared. So some things I like to note is that if we start out with the sum of cubes, then this first factor is also going to be a sum. But in the second factor, in front of our second term, we're going to have the opposite sign. So it's going to be a minus. And of course, b squared will always be positive. So similarly, if we have a cubed minus b cubed, then because I've got this minus here, in my first factor, it's going to be a minus b. And then in the second factor, it's going to be a squared plus ab plus b squared. But probably one of the more important things before we can even apply the pattern is to recognize that we do have a difference of cubes or a sum of cubes. We've got to recognize that the things that are in these positions are perfect cubes. So with that said, it would be helpful if you're familiar with some numbers that are perfect cubes. Obviously, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, 9 cubed is 729, and 10 cubed is 1000. So if you see any of these numbers, then you probably might want to think about trying to factor with a difference or a sum of cubes. So it would be helpful if you're very familiar with these values. Of course, it could go beyond this, but these are probably some of the more common values that you might see. All right, so let's take a look. In IXL, it's going to ask you to find the binomial that completes the factorization. Okay, so again, the first thing I want to do is recognize that I've got a perfect cube. Do I have a perfect cube? Well, I can see that q is cubed. The variable part is usually obvious. But what about this 8? Well, I can rewrite this as 2 cubed. So I have the difference of cubes where my a value is going to be q and my b value is 2. So now that I have that, I'm going to apply this pattern. And we get q minus 2, right? A minus b, so q minus 2. Then we're going to get a squared, so that's q squared. We're going to multiply a and b, and then we get b squared. Notice that this middle term is just a times b. If we were squaring a binomial, the middle term would be 2 times a times b. So that's not the same. Usually, a lot of times this thing will not be factorable because this is not 2 times a times b, it's just ab. And again, in our case, a was q and b is 2, so we get 2q in the middle. So the answer for this question in IXL is q minus 2. I like what they're doing here in IXL. For the first several activities, they have you identify the binomial, right? This a minus b part. And a little bit later, they have you identify the trinomial for this factorization. All right, so here's another. We've got x cubed plus 1000. Well, we probably remember that 1000 from that list of perfect cubes. And so this is going to be a sum of 2 cubes. right? X cubed plus 1000, I can think of that as x cubed plus 10 cubed, right? So A in this case is x, B is 10. We get x plus 10, right? That's my A and B, x plus 10. Notice that my plus sign here is the same as what we have in the sum of cubes that we started with. And then here, we've got the minus, right? We changed the sign right here. But this is my A squared, this is A times B, and this is B squared. All right, so to complete this answer in IXL, we would do x plus 10. All right, so here's another one. Now, this one looks a little interesting. Right away, I can recognize that I really don't have the sum or difference of cubes. But if you take a look at it, what we have is a common factor between these two terms. And whenever you're factoring, you should always start by factoring out any common factors. So these two have in common a t, so I'm going to factor that out. Now that I've factored out t, then I see that I have s cubed minus 512, and 512 is one of those numbers that we saw in the list, right? So I'm going to think about my pattern for a difference of cubes. Okay, I can rewrite 512 as 8 cubed, right? And so if we apply the pattern, we're going to get t times s minus 8, that's my a minus b, and then here we have a squared plus ab plus b squared, or s squared plus 8s plus 64. All right, so here's another one where again we need to think about any common factors that we have, and what they have in common is w. So I'm able to factor out the w. We get v cubed plus 125. Okay, so we got the sum of cubes. 125 is in that list. It is 5 cubed, right? So from here we can apply our pattern. Okay, if my a is v and my b is 5, then we're going to get v plus 5, and then v squared minus 5v plus 25. All right, so here's where they switch to the other side, but it's still the same process, right? We're just answering with a different piece of it. So here again, in this early activity for me, when I went through IXL, what they were doing really is just having you recognize the pattern. They've just changed the variables. So this is just kind of forcing us to recognize the pattern. And again, if we've got a difference of cubes, then it's going to be a minus b times a squared plus ab plus b squared. Or in terms of v and w, it would be v minus w times v squared times v times w, not times, but plus v squared plus w squared. Okay. All right, so yes, that's all we have to do for that one. This last part, the trinomial, would be our answer. All right, so here we're going to do it again. And they've already given us a really good hint, right? When we look at what they have here, we can see that they factored out a 2. And looking at it, if we're working it kind of on our own, we see that we need to factor that 2 off. It's common to each term. And so we've got v cubed minus 64. 64 is a perfect cube. Okay, it is 4 cubed. So if my a is v and my b is 4, then this is going to be v minus 4 times v squared plus 4v plus 16. All right, here's another one. This time, I don't know, you might not think about it, but we can still factor a q from each of these terms. And when we do, we're left with q cubed plus 512, right? So I'm going to use my pattern for the sum of cubes, okay? And my a value is going to be q, my b value is 8, and so we get q plus 8 times q squared minus 8q plus 64. All right, so now in the second activity, the instructions change. You're going to do the difference of cubes, but we have to solve this. We want to find the values of p that make it true. So what we've known or found about polynomials and their solutions is that over complex numbers, the number of solutions is indicated by the degree of the polynomial. This is a third degree polynomial, and so we can expect that we're going to find 3 solutions. It's possible that some of those solutions might be repeated. And if that's the case, we count each repetition of a factor as a solution when we're trying to match it with the degree. But we know that we're going to be looking for 3 different solutions. So we've got p cubed minus 27, and I've already factored this out using our pattern, right? I recognize that this was a difference of cubes. A is p, b is 3, so we have p minus 3 times p squared plus 3p plus 9, right? This is a times b, and this is b squared. Okay, all of this is equal to 0. So we're going to use that 0 factor property, and we get p minus 3 equals 0, or p squared plus 3p plus 9 equals 0, right? I set each factor equal to 0. Okay, over here we get p equals 3, all right? Graphically speaking, what this means is that we're going to have an intercept at 3, 0, and of course we're going to cross the graph at 3, 0 because this has a multiplicity of 1, unless somehow we find another factor of p minus 3 over here, which I don't think we're going to do, all right? So what am I going to do with this then? If I cannot factor it, so we go back to everything that we learned about solving quadratic equations. If you feel like it, you could complete the square. But what I'm going to do is use the quadratic formula. All right, so in this case, we've got minus b plus or minus the square root of b squared minus 4 times a times c. All right, all over 2a. All right, where in this case, a, b, and c are the coefficients of the squared term, the p term, and the constant, respectively. Okay, so when I go on and simplify that, we get p equals negative 3 plus or minus the square root of negative 24 all over 2. And I can reduce 24, right? 24 is 4 times 6, right? But I've got that negative. So the square root of negative 1, that's represented by I. The square root of 4 is my 2, and 6 stays beneath the radical. All right? And so we're here. We can't go any farther unless we distribute the 2 to each term individually. So we could say minus 3/2 plus or minus I root 6. Or for me, I'm going to leave it like this. Yes, we'll leave it just like this and enter that. You may have to tweak that, though, to see exactly how IXL wants you to put in that answer. All right, let's look at one more. Okay, here we have 8x cubed plus 1 equals 0. Okay, so again, we're going to factor this because it is the sum of cubes, right? We've got 8x cubed. I can think of that as 2x cubed, right? My a value is 2x, my b is 1, all right? So that's why we have 2x plus 1 times 4x squared minus 2x, right? If we multiply a times b, we get minus 2x, and then we get 1 squared, which is still just 1. So I'm going to set each of these factors equal to 0. We get x equals negative 1/2. And then again, I'm using the quadratic formula. All right. And so we get 2 plus or minus the square root of negative 2 squared minus 4 times 1. All right, that's my 4 times a times c all over 2 times a. And so we get 2 plus or minus, this came down to negative 12, right, because this is 4 minus 16. So that's negative 12 all over 8. And we get 2 plus or minus 2i root 3 all over 8. Okay, why is it 2i root 3? 12 is 4 times 3. So the square root of 4 is 2. We got rid of the square root of negative 1 by using I. We replaced it with I. And then the 3 stays beneath the radical. Now in this case, I can go a little bit farther in order to simplify it, because I can factor a 2 from my numerator and a 2 from the denominator. And in that case, they cancel out. So if we were to factor 2 from the numerator and denominator, we're left with 1 plus or minus I root 3 over 4.